Dr. Kyra Gan, an assistant professor of operations research and information engineering at Cornell Tech. Prior to joining Cornell, he was a postdoctoral fellow in the Department of Statistics at Harvard University, working with Dr. Susan Murphy. She obtained her Ph.D. degree in operations research from the Tepper School of Business at Carnegie Mellon University, and her interests include adaptive online algorithm design and robust and efficient inference and causal discovery.
Right, so let's pivot the topic a little bit to non-neural network related area. So can I just get a sense how many people know about causal inference? You, okay, that's great. Okay, so I'll probably quickly go through the beginning. So we all know that association does not equal causation, right? What does that mean in prediction problems? Is that oftentimes, right, in medical applications, we see zip code is a predictive feature, for example, for the 30-day hospital readmission rates. However, zip code does not cause the person to get readmitted, meaning that if I just artificially relocate the person to somewhere else, they still have this likelihood of getting readmitted in 30 days. So an alternative explanation is that zip code is a proxy for the socioeconomic status of the patient, and that's the underlying reason why the person is getting admitted. So now there is really big an emphasis of thinking about causality and what's the cause of a particular disease in the domain of healthcare, and that's what I work on. So I usually work with small data regimes, both in experimental studies and also in observational studies. So what is causal inference in observational studies? Right, so here we're interested in estimating the effect of a treatment on a potential outcome, right? For example, a disease. To give you an example of this is that for example, I would like to know what's the treatment effect of a particular drug for treating colds. Say I have a cold, how do I estimate this treatment effect? In an ideal world, I will look at the difference when I take the pill versus I don't take the pill at the same time. So causal inference is precisely hard because you don't observe those two quantities at the same time. So how do people do this? So we, in general, when I talk about causal inference in this talk, you should think about this as the average treatment effect across the entire population, right? So how do we do this? Causal inference fundamentally breaks down into two parts. First part is we need to identify the causal model of interest, and the second part is then perform the inference based on the model that we have, right? So what do I mean by identify the causal model of interest? What are the methods that people have been using historically for identifying this? Mostly falls into the two categories, right? So the first category of causal inference approach assumes an underlying graphical model of my data generating process. You'll probably see some causal diagrams. When you read a causal inference paper, that's the data generating distribution they're assuming. Once you have assumed this causal structure, you can now write down what treatment effect is as a function of the data generating process. And so this is a semi-parametric approach. Then I'm going to empirically estimate what this data generating distribution is from the data and plug into my expression for the target parameter and obtain an estimate. Okay, so this whole line of literature in inference really focuses on the second part. When I do the plugging estimation, how do I de-bias the kind of, how do I make sure that my plugging estimate have asymptotically nice behavior? And I want to highlight that recently we have a paper on this topic, which automatically biases the plugging estimation without the manual derivation. If you're interested, please check it out. So another set of methods that are more common or like you're probably more familiar with in causal inference, it's basically I'm going to assume the underlying causal model is linear, right? For example, I assume the alpha is a linear function of the treatment and some covariance, and I assume additive difference. So once I have this, I can apply the inverse constraint for the robust estimation to obtain the causal estimates. So those are two different approaches. So where does causal discovery kicks in this picture, right? Where does causal discovery help is for the identification of the graphical model. So I really think about the power of causal discovery. The context of inference really sits in the first approach, where we can actually learn what's the underlying data generation process from the data with minimal assumptions. So here I'm not going to make any assumptions on the data generating mechanism. So how familiar people are with graphic models? Very good. Okay. Okay, let's again quickly go through what graphical models are, right? Again, we like to think about graphical models as a tool to model the data generation process, right? You see all those graphs are directed acyclic graphs, meaning that the edges do not form a cycle. So just to highlight that in the causal graphic model for later network study, we like to call the cause of another variable as the parent, right? And the end of that as the child. And we also like to call the child of the descendant of the ancestor. Okay, so those are the standard terminologies. So why can graphical models model or represent the data generation process? It relies on a few assumptions. Just to refresh your mind on the set of assumptions needed, right? The first assumption is the Markov assumption, which states that given the parents of a node in a DAG, right? If you will recall, in the previous node, meaning like if you look at the B node, the parent of B is A here, right? So what this Markov assumption says is given the parents of X node X in the DAG, this node is independent of all its non-descendants. Meaning if A has another parent right in the previous graph, then B would have the independent of the parent. So what's the consequence of this Markov assumption is that it enables the factorization of the data generation process based on the graphic model. So now I can look at a graphic model and I can write down what's the data generation mechanism just by looking at it, right? The way it goes is I look at each individual node in my data set, and the entire joining distribution is characterized by the product of the conditional distribution of each node on its parents. Now, what's the second assumption that we need for representing the data generation process is the minimality assumption, which says in a graphic model, if two nodes are adjacent to each other, then this has to mean that X is dependent on Y. Okay? Just to formalize what's the picture that you have in mind is that first they have Markov assumption in a graphic model. This establishes the statistical independence between the variables. And once I have the minimality assumption, this establishes the statistical dependency between the variables. Okay. So what does this have to do? Anything to do with causality? Okay, so the way that we're going to tie this model to a causal model is by giving the meaning of those edges. So here we're going to say a directed graph. Every parent is a direct cause of all its children. So now with this causal edge assumption, we establish causal dependence. Right? So the DAG is no longer just describing the data generating process, we're describing the cause of one variable to another. Okay. What is causal discovery trying to do? The causal discovery trying to learn this data generating process has the causal meaning from the data itself. So we're going to use a data-driven way to infer the underlying causal structure from data sets with minimal assumptions. So how do we do that? It relies on the following building block. We are going to look at the basic structures in graphical models and look at what are the statistical independencies does that structure imply. And in the end, we're going to use the set of statistical independencies to learn the underlying causal mechanism. So here in the graphical models, so in two nodes, right, the scenarios are very simple. If I have two nodes, one relationship, one possible relationship is those two nodes does not have relationship with each other, or one causes the other. So nothing special about this. So people like to talk about the most basic building blocks in graphical models as the following three node nets. Okay. We're now trying to enumerate all the possible relationships that three different variables can have from the graphical perspective. So the first one that we're going to focus on is what we call the chain. What does that mean? Is that x1 causes x2 and causes x3. If you are familiar with causal inference, what we call this node x2 is a mediator. And so mediator is defined with a pair of variables, x1 and x3. So why we call it mediator? Is the effect of x1 on x3 is only mediated through x2. Meaning that if I intervene on this node x2, x1 now cannot affect x3 in any sense. Right? So just by this definition, what we see is that if I don't do anything, x1 is statistically dependent with x3 because they're causally related. And now once I condition on the middle node x2, I have statistical independencies between those two variables, x1 and x3. And you can actually check the correctness of the statistical independencies purely from the Bayesian factorization. Okay, so that's something that's very easy to do. Now, what is the second structure? It's called work, meaning that my variable x and x2 now causes both the variable x1 and it also causes the variable x3. So it's called x2 is called a confounder between the pair of variables x1 and x3. So intuitively, because x2 is the common cause, it's also going to satisfy the first relationship, right? x1 is statistically dependent with respect to x3. And once I control for the common cause, those two will become statistically independent. So the fork and chain shares the same statistical dependencies. So what is special in this building block, right? The asymmetry actually happens when you have to follow the structure, meaning that, or in the graphical model language, people sometimes like to call it inequality. I don't know why they make this thing. So basically, x1 is the cause of my node of interest x2, and x3 is also the cause of x2. And here's an example, right? Intuitively, let's understand what are the statistical dependencies implied by this graphic model. So say that x2 is traffic. I want to know whether I'm going to run into traffic today. What is the cause of traffic? Whether today is a holiday. The second factor that can cause the traffic is the hour of the day, right? So if you look at holiday and hour of the day, of course, they're statistically independent of each other. There's nothing, those two variables has nothing to do with each other. So you have the first condition that x1 is independent of x3. Now, once I control for the traffic, say given at the moment I don't have traffic, what does it imply? It implies it cannot be a holiday and it cannot be a rush hour. So now when I condition on the node x2, I get statistical dependencies, right? So I have this conditional dependence between x1 and x3 when I condition on x2. Okay. So those are the three basic structures. And again, this node x2 here is called a collider. Things get a little bit more interesting. You thought maybe that's all we're going to cover in this case. Okay, so there's one more thing. In a graphical model, some funny behavior, so you have the one condition on the descendant of the collider. Okay, you would expect, oh, this is the descendant of the collider. It doesn't affect, right, the three node structure here. So condition on the slope should not change the original independence relationship inferred by those three loci. However, that is not true. Okay? Because x4 is a descendant of the glider. If I control for this variable, it's actually going to affect the variables that x2 can take, right? So for example, what's the example of x4 is whether you're late to work, right? Whether you're late to work is a result of traffic. So I know that if I am late to work, that's by conditioning on x4. What does that imply? That implies there is traffic. With high probability, there is traffic, right? So by conditioning on x4, you're kind of implicitly conditioning on this variable x2. So you get the following condition that x1 and x3 actually becomes dependent with each other, even if you condition on the descendants of the. Okay. So that finished all the fundamental pieces of graphical model building blocks. What we are going to talk about next is the deseparation, and that's the rule that's going to enable us to learn the graphical model from the data. Okay. So what is the path, right? If you look at the model that we saw previously here, right? A path is any combination of the edges that are connected to each other. Now I say that a path between a pair of variables x and y is blocked by a set p if and only if the following condition holds, right? One of the following condition holds. What does it mean by blocked? Simply means that I have conditional independencies between the node x and y. And how do I do that? Is that if the set of if along the path, there's either a chain or a fork around this variable w, where that w is inside this condition set, then this path is blocked, right? So going back to the previous example, here with respect to x1, x2, x1, x4, x2 is a chain, right? It's on the chain. So how do I block the path between x1 and x4? I condition on x2. So that's what the first condition say. What is the second condition? Is that if naturally W is a collider on the path and it's not conditioned on in the variable set Z, and none of its descendant is conditioned on this set, then I also block this path. Okay, what's that natural example here is that the path from x1 to x3, but I can travel from x1 to x1 to x2 to x3, but x3 is not conditioned on, then this path is blocked. Okay, so that is the definition of a blocked path. Any questions? Now, what is deseparation? Deseparation simply says that two variables x and y are deseparated by a set of variables c if all the paths between those two variables are blocked by my set c. Okay, so that's simply the definition of deseparation. And let's see an example. So I want to, for example, in the following graph, I would like to find a set that deseparates the variable t and y. How do I do that? Anyone wants to try? Right, what does deseparation mean when I have the following graphical structure? I want t to be statistically independent of y. So I need to first find all the active paths are currently inside my graph, right? So here is a valid path that's open because W2 is a component and nothing's being conditioned on this path. So as long as I condition on any one of the W1, W2, W3, this path is blocked. So I need at least one of those three nodes to be conditioning set. I have another path from T to Y through the mediations M1 and M2, right? Without conditioning on anything, I can T1 is statistically dependent with respect to Y along this path. So I need at least one of the M1 and M2 to be in my conditioning set. How about the last one? X2 is a collider for T and Y. So naturally, this, if you don't do anything, this path is blocked because naturally, if you only look at this path, those nodes are statistically independent with each other. If you have to condition on X2, then you have to condition on additional nodes, either X1 or X3. Okay, so if you condition on both X1 and X2, it will still block the entire path. Okay, so that's the separation where we find the set of variables that actually separates those two nodes. Here we go. Yeah.
Different compared to cuts in graph. Cuts in graph. Yeah, I mean, operated graph.
Yeah, I know. So cutting graph is different because cutting graph does not talk about orientation between the edges. For example, here, right? If you are talking about the cutting a graph, maybe you just cut here because the orientation does not matter. It's not tied to statistical dependency or dependencies. But if you now thinking about what each structure corresponds to in terms of statistical dependencies that you would observe on the data, then this would mean that you either don't do anything or you have to block two nodes. So that's the difference. Any other questions? Okay. So what does this have to do with the public discovery? So these operations really the building block of those kind of constraint-based causal discovery methods, where the goal is to perform a sequence of statistical independence tests to detect what is the underlying causal structure. I will give you an example of a very common PC algorithm that people use in the causal discovery literature, and I'll dive into the method that we use in proposed. So one more assumption that we need for discovering the causal structure from the data is the faithfulness assumption. Okay, so what does this assumption say? Is that given a probability distribution over variables, the faithful assumption asserts that statistical independence relationships observed in the data faithfully reflect the absence of certain direct causal effects among others. Okay. In short, you can think about the following picture. The Markov assumption in the causal discovery literature really established the relationship from causal graphs to data. Now, however, I learn from data, I need to assume whatever I observe from the data truthfully reflects the underlying data process. So that's what faithfulness is assuming under the hood. Two more assumptions that we usually read is first, the graph is acyclic, meaning there's no cycles, right? If you think about causes, if I have a circle that goes on and on, how do I distinguish the effect of those variables? There's no effect, right? And the last assumption that we commonly meet in the causal discovery literature is causal sufficiency condition. What does it mean? Is that my variable contains all sufficient information that enables me to learn the underlying data generating distribution. Okay? This simply means there's no observed confounders in my data set, if you know what that means. Okay? I want to highlight that the algorithm that we propose does not rely on this causal sufficiency condition because for like the classical PC algorithm, this is required. So let's talk about one more concept of markov equivalence, and I will use sketch of what PC algorithm is and give an example how you would run PC algorithm or data sets. So we see from the previous examples that the chains and the fork structure include the same statistical dependencies, right? If you read the graph and kind of parse all the conditional independence kind of implied by each one of the structure, you will get a whole set of the conditional independence, and they're the same among all the structures. So we call the resulting graphs that share the same causal independencies as they're in the same Markov equivalence class. Because at that point, no statistical independencies can distinguish between those models using independence tests. Okay? I want to highlight there are score-based methods that can potentially distinguish between those structures, but that's the beyond scope of this one. Now, what's so special, again, is about this V structure. It really is the key observation why, or key kind of observation why causal discovery works. Okay? So again, V structure shares a very unique statistical dependencies among the structure, and you can see for these structures, the Markov equivalence class is unique. I cannot come up with another set of variables, so you know, kind of a structure that shares the same statistical dependencies as the structure. So this really kind of hinges on how a causal discovery algorithm can be potentially kind of sketched out. Okay? Among the variables that are Markov equivalent, you can observe that they actually share the same skeleton of the causal structure, meaning that if I remove the orientation between the variables, they actually share the same overall structure. Okay, and now if I give you this graph, how do I know that this graph is different from this class of variables? You will see that the additional graph actually has kind of has a different statistical independence as in Markov equivalence class here. Okay? So that's the key underlying observation, is that if two graphs kind of shares the different skeletons, then they have a different set of statistical independencies and dependencies associated with them. Okay? And that's the key insight. How do you learn what's the structure of the underlying graph? Okay. So again, two quantities that we're going to rely on in learning the causal graph. The first one is the V structure, and the second one is the skeleton. And the causal graph model, graphical learning model, simply first trying to learn what's the skeleton of the underlying data mechanism and trying to orientate the rest of the edges. Okay. So there's a theorem early 90s saying that two graphs are Markov equivalent if and only if they have the same skeleton, have the same V structures. So here's the sketch of the common PC algorithm, right? So here's the graph that we're going to create from data. How do I start? I start with a complete undirected graph. And what I'm going to do next, I'm going to search through whether I achieve statistical independence between A and B by conditioning on a subset of nodes. Once such a node exists, I know I can remove this particular edge. Okay, so I'm going to do this step iteratively until I'm kind of left with the skeleton, right, of the underlying causal graph. Then I'm going to identify what is the V structure because it satisfies a different statistical dependence test. I'm going to use that to orientate the edges, the V structures in the graph. The last step is simply to orientate the rest of the graphs, the rest of the edges that are adjacent to the V structure, right? Because in the previous step, I already identified I have only one V structure here. I know this cannot be a V structure, so there's only one natural way that I can orient that there. Now, what's the problem with this approach? As many of you might already know, that this is not computationally tractable, right? To search for the number, the conditioning set that separates those two nodes. In worst case, you need to condition all the rest of the nodes iteratively, right? So the worst case time complexity for searching the skeleton itself is exponential in the number of variables that I have in my data set. So that's one of the main reasons. The second reason is that it requires a lot of samples, right? How many samples do I need to estimate a conditional probability law? That sample set grows exponentially in the number of variables I'm conditioning on. So that's the intuition why probability discovery requires a lot of samples. And the last thing that I want to highlight is that if in the end my method returns a Markov equivalence class, right? I don't know whether this is mediated or it's a confounder. That's actually problematic in my downstream inference task because I don't know which node to condition. Okay. So just to give you an example where causal the algorithm fails, right? Here is the raw data that we generated. It's only 10 of that. 10 of that. Okay. So for the 10 of that, we tried 10,000 samples on PC, and you can see even with 10,000 samples, PC does not return the correct results. Okay. And similarly, there's a version of global discovery algorithm out there that does not rely on the causal sufficiency assumption, meaning some variables can be missing in the underlying data generation process. So again, here's an experiment where we have access to the underlying CHOW model, and we start iteratively dropping some nodes. And you can see the algorithm, even with 50,000 samples, it does not return meaningful outputs. Okay. So really, this really prompts us to kind of design a new discovery algorithm that is tailored towards the downstream inference task. Right? If you think about, I still want a global discovery algorithm. Where can we cut corners? Probably is nowhere, right? And those are the necessary steps for me to get the entire causal structure. Now, if I care about inference, I only need to estimate what treatment effects are. Then I don't need to learn the entire graph. I only need to find the variables in my data set that are relevant for my causal estimation in the downstream inference task. Okay. In other words, we are going to use this notion of a valid adjustment sets in the causal inference literature. So what does this valid adjustment sets mean? Simply it blocks all the non-causal path between my exposure and outcome variables. And if I know the set of variables, it is guaranteed that I can get the correct causal estimates. All right, so the problem here is really designing a causal discovery algorithm to discover the set of valid adjustment sets. Right, just to give you a more concrete example, what do I mean by causal association? Is that if you have a confounder, then the flow from the treatment to the outcome to the confounder is a non-causal association because that flow is created by a cause. If I have a mediation, this is a causal association, so I don't want to block this path. Okay? If I have a colliding path, I just don't want to do anything on it because if I naturally don't do anything on it, it's blocked, right? I don't incur additional spurious association between the two. So let me just give you the high-level idea. What we're proposing in this local discovery by partitioning approach is that we actually observe by a very simple observation that I will show you in the next slide, that the variables can actually be defined relative to the exposure and outcome. So I can define what a variable is simply using its relative position to the exposure and outcome, and I have 8 such partitions. Okay, so we come up with a independent task-based method that performs this eight partition. We first show that this taxonomy of the partitions is exhaustive and mutually exclusive. Then we propose a new algorithm to learn the partitions. So there's no skeleton learning, no edge orientation involved at all. The end goal is simply to identify what are the set of variables in the value adjustment set. Okay. One more thing I want to highlight is this method is actually robust to probability sufficiency, meaning in some part of the structure, if there is an observed confounder, this method is going to work. So the simple intuition that you would observe here, X is my exposure variable, Y is the output variable of interest. Now I can kind of enumerate all the possible relationships that the third node can have with respect to the exposure and the output. And those are the 8 building blocks of the algorithm. Simply, we want to distinguish between those structures. And you see our algorithm iteratively trying to identify what each category of the variables are. I'm going to skip the theoretical results of the work. You can look it up in the paper. And I want to talk about the performance. Okay. So what's the result of this local partitioning approach? It's first getting time efficiency. So instead of having worst case exponential runtime complexity, here our worst case runtime is quadratic in the number of variables. And you can see the side in the nice, right? Empirically, you can see this is the performance kind of number of tests performed by the TCL algorithm. This is the number of tests performed by LPP on local benchmark. And similarly, by the fact that we're conditioning on less variables inside each iteration, we gain sample efficiency. So now we are able to run the correct value adjustment set with less samples than the traditional PC or global discovery algorithms. And the last one is the flexibility, right? Because LPP, our local discovery by partitioning approach based on conditional independence tests, and those tests can be non-parametric. So we don't really need to assume any kind of causal structure of underlying the model to discover the value adjustment set. All right. Quickly, right? I claim that this is the method that we developed for inference. So how well does it do for inference? So the first graph, because for the first set of column of figures really illustrate the performance of several different algorithms on the identification of valid adjustment sets. You do observe that performance on the kind of their both ways of combining or identifying the valid adjustment sets. Second figure is the bias, or I think it's what's the true value of the average treatment effect. So the dashed red line here overlaps with our estimate. We can see our estimate is unbiased. And for the last figure, what's the variance of the resulting estimate? You also see that our proposed procedure has the worst variance, simply because the value adjustment set is much smaller than the ones identified by the other. Okay, so that concludes what I want to cover. Thanks.
So I was wondering what you think of the big forward or some ways that possible discovery contribute to drug development and clinical research.
Well, I think so. First of all, this LDP does significantly decrease the number of samples required. Maybe like if it's still enough for us to deploy this method on large scale data set, is unclear, right? I mean, it's a huge improvement, but I think there's a lot more rooms that are left that you can potentially reduce the time for the sample complexity is very underlying. So I think people like one big challenge in causal inference in observational studies is the identification of the valid adjustment set. Right? Without that, people need to make strong assumptions to So I think, I mean, I would encourage the community to try this method and let us know what is not working and then we can keep it moving.